All right, I think we're ready to get started. It's my pleasure to introduce Jennifer Balakrishnan for the first of her 4 lectures.
Well, thank you very much. It's a great pleasure to be here. This course is on computational tools for quadratic Chabauty, but I thought I'd first start with some computational tools for the Chabauty-Coleman method. And to motivate that, though of course we've already seen some very nice motivation today, I thought I'd ask this question. So here's a question. Does there exist a pair of a rational right triangle, so right triangle with all rational sides, and a rational isosceles triangle that have the same area and the same perimeter? All right, so here are some triangles. So here's our right triangle. And here is our isosceles triangle. And let's rescale. So we'll assume that L is 1. So we want to understand this over the rationals. So we're going to suppose that we have K, T, and U, some rationals, and T and U are between 0 and 1, and K is positive. So we compute areas and perimeters and equate them. So for areas, we get K squared T, 1 minus T squared, is 2U, 1 minus U squared. And for perimeters, we get K plus KT is 1 plus 2U plus U squared. So we'd like to solve this system. And then we do a bit of algebra. So combine these 2 equations and then make a small transformation. So this gives us that there is some rational x such that the following is true. So 2x k squared plus minus 3x cubed minus 2x squared plus 6x minus 4k plus x to the 5 equals 0. All right. So now we notice that we have a polynomial in K, and its discriminant must be a rational square. So we have that y squared is this cubic term, minus 3x cubed minus 2x squared plus 6x minus 4 squared minus 4 times 2x times x to the 5th. And if we rewrite this a bit, here's what we get. And we have a genus 2 curve. And we want to know its rational points. So what can we say? So let's call it x. So we'd like to determine the set of its rational points. So it turns out that so the Jacobian J of x has rank, more del rank, equal to 1. And this we can ask Magma to do. Magma tells us this one. And also, the Chabauty-Coleman bound. So this you heard a bit about in David Zurich Brown's lecture. So the Chabauty-Coleman bound here gives that the number of rational points is at most 10. So let's look for some rational points on this curve. So we can find the following. So we have some points at infinity, and 0 plus or minus 4, 1 plus or minus 1, 2 plus or minus 8, and 12 over 11 plus or minus 868 over 11 cubed. So we've found 10 rational points. So we've determined the set of rational points here. And the answer to the triangle question, so this is a theorem of Hirakawa and Matsumura, who were graduate students at the time, so this is from 2018. The answer is yes, there's exactly one pair. All right. So we heard a little bit about Coleman's effective Chabauty. So let me just put this bound up here again. So this is Coleman's version of effective Chabauty. And this is what I mean when I say the Chabauty-Coleman bound. So I have x over q, a nice curve, and the genus at least 2. And I'll suppose that the rank of the Jacobian is less than g. Now, if p is greater than 2g is a good prime, then we have the following, that the number of rational points is bounded above by the number of fp points plus 2g minus 2. And as we heard this morning, bounds like this come from understanding the number of zeros of a p-adic integral. So this bound comes from bounding the number of zeros and we call these integrals Coleman integrals. All right, so let me tell you a little bit about Coleman integration and how to compute some Coleman integrals. So Coleman gave a theory of p-adic line integration. In a series of papers in the 1980s. And so let me give you some nice properties of these integrals. So I'll assume that my curve is over QP. And I'll focus on the case of good reduction, just to simplify some of the statements here. So the p-adic integral so from p to q of omega, this is something in qp bar. So this is defined for points p and q over qp bar and some regular one form. So we'll talk about other differential forms you might want to integrate. It satisfies the following. So first, the integral is linear in omega, so we can split things up. We have a way to compute tiny integrals, or integrals that are essentially local. So if I have points P and Q that reduce to the same point P bar and XF P bar, then we call the integral a tiny integral. We saw a little bit about tiny integrals this morning. We can evaluate it through a local computation, picking a uniformizing parameter, and then rewriting the integral in terms of that uniformizing parameter, and then integrating a chaotic power series. All right, so we also have the following property. So if I have an integral from P to Q, and then an integral from P prime to Q prime, then I can kind of mix up the endpoints. And what this tells me is that we can define an integral omega along a divisor of degree 0. So point Qj minus Pj. So this is in div 0 over Qp bar. And we define this as a sum of integrals. So, wrong order. So Qj, Pj, omega. If I have d principal, then the integral of this regular 1 form along a principal divisor is 0. The integral is compatible with Galois action. And if I fix a point, P naught, and I have some non-trivial regular 1 form, then the set of points P that reduce to a fixed point on X FP bar such that, move it up, sorry. Is that okay? Thanks. Such that this integral vanishes is finite. All right, and we call this the Coleman integral. All right, so as a corollary, given the hypotheses of our previous theorem, I'm going to fix a base point over QP, and I'm going to use that to embed our curve X into its Jacobian. So I'm going to send a point P to the class of this divisor, P minus B, and we have this map from QP points on the Jacobian paired with regular 1 forms on the curve. So this pairing is takes values in QP. And this is additive in Q, and QP linear in omega, and given by integrating. So integrating omega along D for some divisor that represents this point. So also I should mention, if I have some point P on the curve, we have, so I'm just going to name this the Abel Jacobi morphism with base point, so AJB, that takes P to the linear functional. So the integral given by integrating from our base point B to P of omega. So this is AJ BP. All right. So we also heard this morning, so just to kind of give you a recap of some other things that will be useful for us. So the Chabauty-Coleman method uses a certain space or a certain subspace of the space of regular one forms. And we're going to now assume that we have a rational base point and use it to embed x into j. And so we'll call this our subspace of annihilating differentials. And I'm going to call it A and not B. But A here is, so the set of all omegas such that for all points on my Jacobian, this pairing is 0. This is the subspace of annihilating differentials. Okay. So our main goal in computing with the Chabauty-Coleman method is to compute annihilating differentials and then understand them to compute rational points. All right. So let me just produce this diagram. So we have the following. So we have rational points on our curve and 2 QP points on the curve. And then rational points on our Jacobian, QP points on our Jacobian. We have the space of regular one forms on our Jacobian. Dual space of linear functionals. Let's try to squeeze this in. Same thing on the curve over QP. All right, and this is our log map, and this is Abel Jacobi with base point. So what I mean by computing rational points via Chabauty-Coleman is the following. We mean compute the finite set of p-adic points. So I'm going to name this, since this and subsequent generalizations will play a major role in what we want to study. So the set XQP1, this is the set of all p-adic points Z, for which all integrals of our annihilating differentials omega vanish. So A, again, being the subspace of annihilating one forms. And by construction, the set of rational points is contained in the set XQP1. Okay, so the first question that I'd like to answer is how do we compute XQP1, or how do we construct annihilating differentials in the Chabauty-Coleman method? So here is an example. So we'll take x to be this curve. Y squared equals x to the fifth minus 2x to the third plus x plus a quarter. And it started off, it's from the LMFDB. It's 971A 9711. So in the LMFDB, there's a wonderful database of genus 2 curves, thanks to work of Booker, Seisling, Sutherland, Voigt, and Yasaki. And I did a small transformation so it looks like y squared equals f of x. And the label here tells you about the conductor and the discriminant. So this is a nice genus 2 curve to try to do some experiments with. So here are some facts about this curve x. So we can look for rational points up to some height bound, search in a box. And if we do that, so I'll call that xq known. So we have a point at infinity, and then 0 plus or minus a half, minus 1 plus or minus a half, and 1 plus or minus a half. All right. What else? So the Jacobian is simple. And also, it's of rank 1. And there's no torsion. We can find a point of infinite order, so supported on rational points on the curve. So taking this point in the Jacobian, this has infinite order. Okay, something else. This curve is good at 3. And 3 is a small prime. So we have some hope of running the Chabauty-Coleman method on this curve. So let's compute xf3 here. And we can see that it's 7. All right. So I used Stoll's bound, the Stoll's refinement of Chabauty-Coleman here. So remember Chabauty, the classical, like the effective Coleman bound, we need P to be greater than 2G. So that won't work. So let's use what Stoll did. So for P equals 3, we get that the number of rational points is bounded by the number of FP points plus 2 times the rank plus this factor, the floor of 2R over P minus 2. So in our case, this turns out to be 11. So we know 7 rational points, but the upper bound is 11. So as David mentioned, now we need to do something a little bit more refined and actually look at some p-adic power series and study their Newton polygons and see what we can say about the number of zeros that they have. So we need to do more work. So what we'll do is we'll construct a 3-adic annihilating differential and well, at basis of the space of regular 1 forms, this is the genus 2 curve. So this is just given by taking x to the I dx over y, and I have an extra factor of 2 in the denominator there. So x to the I dx over y for I equal 0 and 1. So our eta is a Q3 linear combination of these two elements, omega naught and omega 1. So what we'll do is we'll compute some p-adic integrals and use that to compute our annihilating differential. So we'll use the values of omega naught along this divisor. So -1, -1/2 is this point of infinite order that we wrote down. And maybe I'll call that alpha. And beta, which will be integral of omega 1 along the same divisor to compute beta. All right, so at this point, we open up Sage. And we press a button or a few buttons. And we compute alpha and beta. And three-adically, I'll just give you a few digits. So alpha is 3 plus 3 squared plus 3 to the 4th. And some higher order things. And beta is 2 plus 2 times 3 plus 2 times 3 cubed, plus more things. And so we have this one-dimensional space of annihilating regular one form. So we just take one of these combinations, so something like beta omega naught minus alpha omega 1, and run Chabauty-Coleman. Okay, so at this point, the question is, how do we get these numbers? Right, these are three-adic numbers that we just kind of pulled out of thin air. So let me explain where those numbers came from. Yeah. Oh, sure. From the fact that we have these locally analytic functions, and they have finitely many zeros in each residue disk. So the same argument that David gave earlier today. So we're constructing some non-zero regular one form, and within each residue disk, if we integrate it, it's going to have finitely many zeros, and then we have finitely many residue disks. So locally, these functions are, so this idea, sorry? So essentially, they're logarithms. So it's integrals of regular one forms. And locally, this is some p-adic power series. You write down a uniformizing parameter, and you can use that to uniformize your unit disk. Again, using that isomorphism that David wrote down this morning. So it's, yeah.
Could you repeat the question? I can't hear any questions.
I think the question is, why is the set finite? Is that right? So the question is, why is the set XQP1 finite? And my claim is, we're constructing, so we're writing down the integral of a regular one form, and that's locally analytic within each residue disk that has finitely many zeros, and altogether there are finitely many residue disks. So altogether that gives us finitely many p-adic points. All right. Yeah. Sorry? Oh, sorry. So this is the base point B that we fixed. So I guess, yeah, part of the question is there's a global constant integration that we need. So the integral, so we're fixing one base point and then varying across all residue disks. So to get to each residue disk, we'll need to have some constant integration. And that constant integration will come out of what I'll describe shortly. But there is some variation across all residue disks. Are there other questions? All right. So where do these numbers come from? All right. So I want to say a little bit about explicit Coleman integration. And I'll give one viewpoint, though there are a few different ways to compute Coleman integrals on curves. So this will be using the action of Frobenius on p-adic cohomology. Sorry, is that better? Okay, thank you. So using the action of Frobenius on p-adic cohomology, I should mention that we can also work in the Jacobian of the curve using the kernel reduction and reduce the computation to that of a number of tiny integrals. But that approach doesn't have an obvious generalization to the iterated integral setting that we'll also need to talk about in quadratic Chabauty. And since we would like to say things in as much as we can a Jacobian-free way, let's try to do that here. So maybe I should also say before I get into the details, if you're curious, there are implementations of these algorithms available. So you can do this in Sage natively for hyperelliptic curves. Or Magma if you go to a certain GitHub repo for plane curves. Okay, so
one is always better for the other.
what was that?
It's always better to use Magma for plane curves and always better to use
Oh, I don't know. So the Sage implementation has been out for about 10 years now, so it's fairly robust. This was work of Robert Bradshaw, Kieran Kabaya, and myself, and maybe some others along the way as bugs have been found and so on. And so a lot of people have tested this implementation. The Magma implementation is new, and it's not in the Magma kernel. It's in a GitHub repo that Yad and Tautman and I maintain. And so I encourage people to test it out with their favorite plane curves and let us know about the bugs that you find. But I think if you have a curve that's not hyperelliptic, certainly that's a good thing to try.
It's also worth advertising that Sage implementation for hyperelliptic curves, the first pieces of it were actually written during the Arizona Winter School.
Oh, that's right. Yeah, the 2007 Arizona Winter School is where this started. So yeah. All right. So I'm going to let XAN denote the rigid analytic space over QP associated to my curve X. And I'm going to want to integrate over a wide open subspace of XAN. So this is the complement in XAN of the union of a finite collection of disjoint closed disks of radius less than 1. And before we get further, let me enumerate a few more properties of the Coleman integral. All right, so I'll state this as a theorem of Coleman. So I'll have eta and xi be one forms on a wide open V of XAN, and points P, Q, and R, QP bar points on V, and I'll let A and B be some coefficients. Then this is just slightly more general than what I stated earlier, so we have linearity in the integrand. So if I have my A eta plus B C from P to Q, this is A eta B C. Additivity and endpoints. So I can go from P to R and R to Q. And this is P to Q. I have change of variables. Under rigid analytic maps. So in particular, we'll apply this in the case of Frobenius. The fundamental theorem of calculus. So if I have some df from P to Q, this is f of P minus f of Q. And I also have Galois compatibility. Yeah.
So the question is more about my ignorance. But one thing that's confusing to me as a topologist, upstairs or something, is that the path doesn't matter. I mean, it reoccurs in several places in all these talks, so why?
I think David might say a little bit about this in the case of bad reduction. I wasn't planning to say much about that here in the case of good reduction.
What was the question?
Oh, the question was, why does the path not matter? So in our case, in our setup, this integral implies that if we integrate from P to P, we just get 0. And so why does the path not matter? So the short answer is Frobenius fixes some path for you, and that path necessarily forces this to be true, that the integral between P to P is 0. David might say a little bit more about bad reduction, where there are some log terms and other things that you pick up.
That's what the final two lectures will be about. That's what the final two lectures will be about.
In your lecture? Okay, all right, great. So Minyoung will say something in his lecture as well. All right, so let me just tell you about the strategy for computing these integrals. So we want to integrate, so we'll integrate various flavors of things over the next few days. So today we will integrate one-forms of the second kind on hyperelliptic curves first and then on plane curves. So P to Q, omega, for omega, a one form of the second kind, so residue 0 everywhere. And here I'll assume, just to make things easier, that these are QP points on my curve. And I'll suppose that X is a hyperelliptic curve. So here's a sketch of explicit Coleman integration.
So you mean like have poles?
So I might have poles, say, so say in the case of a hyperelliptic curve, I might integrate something that has a pole at infinity, but it'll have residue 0 there. And, so you might have to make sense of what this integral means with the tangential base point, but we'll kind of hide some of these issues for now. So where we're integrating for now, so tomorrow we'll talk about integrating differentials of the third kind, certainly, which come up in p-adic heights. And so when we have simple poles, we'll have to take a different strategy. But in the case of hyperelliptic curves, we will really kind of just integrate things that look like x to the I dx over y, and those things at most have a pole at infinity. Okay, so this was work that started at the Arizona Winter School in 2007, a project that Kieran Kadlaya had with Robert Bradshaw, and then we extended it to the case of Weierstrass points and some other settings. So we first take phi a lift of p power Frobenius. And we're going to compute. So I'll tell you what that looks like in a second. We'll compute a basis, omega I, of one forms of the second kind. So a basis for H1 de Rham, if you will. And we're going to compute the action of Frobenius on one of these differentials using Kalaya's zeta function algorithm. So counting points on curves using Monsky-Washington cohomology. And we'll use properties of the Coleman integral to relate this. So the integral from P to Q of the pullback of omega I to the integral that we actually want to compute, the integral of omega I from P to Q, as well as other terms, other easier terms. And then finally, we're going to solve for all of the integrals on basis differential using some linear algebra. Okay, so one key step in this is the computation of the action of Frobenius on one of these basis differentials omega I using Kalaya's algorithm. So let me just briefly sketch that. So I'll let x be a hyperelliptic curve with this affine model, y squared equals p of x. And we're going to work in an affine piece where we've deleted the Weierstrass points. And we'll take phi to be the following lift of Frobenius. So we're going to send x to x to the p and y to this. So we're going to compute this binomial expansion for the square root. And the point of writing this in this way is to see that as we take more and more terms, chaotically, this is a sensible thing to do. All right, so you can see the numerator here, this p of x to the p minus p of x, all that to the p. This is going to be divisible by p. And as we take more terms j, this will get smaller and smaller chaotically. Now, we want to use this to compute the action of Frobenius on one of our basis differentials. So remember, we have things like x to the I dx over y. So let's just practice. So we're going to send x to x to the p, so x to the pi. Then we have d of x to the p. And then, well, we'll send Frobenius, we'll send y to where it has to go. So let's just simplify the numerator. So x to the pi, and then p, x to the p minus 1 dx. All right, so this is something like p x to the pi plus p minus 1. And then now we've inverted where Frobenius sent y to. So there's a y to the minus p times the sum. So minus 1/2 to the j, and then all of that to the j. And you can see that this has lots and lots of terms, so actually infinitely many terms, and a pretty bad pole order. And so we need to figure out what to do with this, right? How to reduce the pole order using the relations that we have in cohomology. So maybe another word about why we actually don't work with infinitely many terms. So part of what Chabauty did was to figure out how many terms we actually need here. So how many finally many terms we need here to get provably correct results, first to compute with the zeta function, but also to compute a Coleman integral. How many terms of this expansion for y do we need? And this is something that we can do. So precision analysis, of course, is very important, sometimes very subtle. And I won't say too much about that during this lecture course. Some details are in the notes, but please be aware that this is something that you have to consider, especially if you're making these truncations of infinite series. All right, so we computed the action here, and then now we need to reduce the pole order of each resulting differential using relations in cohomology. Okay, so if we denote the basis so omega I from 0 to 2g minus 1, then what Chabauty's algorithm is going to give us that after we reduce pole orders in an algorithmic way, we have some expression, so some exact thing, some dhi, plus a linear combination of our basis. And so there is a precise linear combination of d's of monomials that you'll take, and each step you'll collect those into this the end, this dhi. And, well, then how does this allow us to compute a Coleman integral? So if we can compute hi and this matrix of Frobenius, then we can write down a linear system whose solution looks like this. So the integral of one of these basis differentials, so say omega I. So this is the transpose of the matrix of Frobenius minus identity inverted, and then some terms here. So this comes out of the fundamental theorem of calculus, minus some tiny integral, so the integral from p to phi of p, and the integral from phi of q to q of omega I. And we can do this because we understand what the eigenvalues of this matrix of Frobenius look like. So we know that they have norm root p by the proof of the Weil conjectures. So we can take this minus identity and invert and get all the values, the Coleman integrals, on our basis differentials. All right. So maybe in the last few minutes, I'll finish the example with the three-adic integral on our genus 2 curve. So this was to say where those three-adic numbers came from. We did some three-adic linear algebra using the matrix of Frobenius and this reduction to get the matrix of Frobenius and this exact form dhi. So with the three-adic integrals on our curve, so we constructed eta, which was, we said, this linear combination of, omega naught and omega 1, where these numbers, alpha and beta, are computed using this linear system star. And we want to compute x, q3, 1. right, so we're going to do this by computing some power series expansions. Of all Coleman integrals, so eta from the space point 0, 1/2 to pt, where this point pt ranges over all residue disks. So within each residue disk, pick some point, write down a uniformizing parameter, and then use that. But maybe there's a really good choice of point to pick for this particular curve. So we're going to take this to pt. I'm going to call this a point p0 in the disk. So this is some three-adic number, and this is a three-adic number, and this is some three-adic series. But there's something very lucky here. For each residue disk, the lucky fact is that for each residue disk, there is some rational point. And we know that if we're going to integrate from a rational point to another rational point, this integral vanishes. So we don't have we have this constant integration. It turns out that we can take it to be 0. So the three-adic number is 0. So now we just have a local computation, writing down a uniformizing parameter at that rational point, and then computing this tiny integral. So computing the tiny integral in each residue disk, we find each just has a simple 0 at the known rational point. And this proves that this curve just had the 7 rational points that we knew about. And I think I'll stop here. Thank you.
All right, we could take a couple of questions.
If the lucky fact here doesn't hold, then is there anything you can do, or are you just out of luck?
So more generally, we would then compute the values of these integrals using this algorithm again. So we would just have some extra three-adic numbers that would play a role. But yeah, more generally, this is just kind of a random coincidence. As I was doing the example, I was like, oh, that's pretty nice, and so I went with it. But yeah, usually you would have some p-adic numbers along the way. Yeah?
You mentioned that you have this theory of Coleman integration between any two QP bar valued points of your curve. Can you extend this to, for example, CP valued points on the curve?
So this course is about computational tools, and I don't really have much I can say, I think, about computing with CP points.
Okay, there's a theoretical framework of...
I think Coleman's... yeah.
Can you say, once you know that it's a simple 0 at each rational point, how did you conclude that there were 7 rational points in the last step?
So we computed within each disk a three-adic power series, and it just had the 1 0 that we knew about, and then something that was non-vanishing. And so we know that the set of rational points is contained in the set of these p-adic points that we found, but the set of p-adic points was precisely the set of rational points. So we're done. So typically that doesn't happen. So typically even after that, so you compute some p-adic power series and then you find some extra p-adic zeros, and then you have to interpret them in some way, or maybe, as David mentioned, use the more delvasive or other techniques to rule out the extra points. But this was, a little bit lucky for a number of reasons.
We don't have further questions. Let's thank Jen again. So we have the evening working sessions back in the hotel. I believe they officially start at 7:30, but the room should be available from 6:30 if you want to get an early start. So that will be in the main ballroom back at the Marriott.